Many times when we're reading a chemical equation, we might just assume that the reactants collide, come together, and immediately form the new products. But very often the reactions will not take place in a single step. There are many intermediate steps that happen along the way before actually forming the desired final product. In this section, we're going to learn about reaction mechanisms. A mechanism describes the sequence of steps that will take us all the way from reactants to products. A single step in a mechanism is called an elementary step. Elementary steps will add up to give us the overall reaction of interest. So they would add up to give us our overall equation. We're going to take a very simplistic view at reaction mechanisms and assume that our reactions have two elementary steps in them. In real life, a lot of reactions could have 3, 4, 5, all the way up to 10 or 20 steps that add up the whole mechanism. If you take organic chemistry, you'll be able to learn reactions that have very many steps in between them. So imagine that we have an overall reaction where we have A plus 2B forming C and D, where A and B are our reactants and C and D are our products. It's highly unlikely that one molecule of A is going to come together with two molecules of B, and they're going to collide with the correct energy and the correct orientations at the same time. So instead of this all happening at once, the reaction happens over two steps. So maybe first, one molecule of A comes together and collides with one molecule of B in the first step. And then we form E and C. C is one of our products, so first we made one of our products. But E is not one of our products. Notice it's not anywhere in the overall equation. So E is produced in one step, and this is called a reactive intermediate, RI for short. A reactive intermediate is a species that's only formed for a fleeting moment. It's made in one step and immediately consumed in another. So the reactive intermediate is just that. It's present intermediately, and then it gets used up, and it's not overall in our equation when we add up the two steps together. So essentially, if we were to add together step 1 and step 2, since it's a product in one and a reactant in the other, or on opposite sides of the arrows, it will cancel out, kind of like we saw with spectator ions. So then maybe in a second step, that reactive intermediate combines with the other molecule of B that we need, and then we form our second product, D, in that second step. So anywhere along the way, if we take step 1 and step 2 and we add them together, we should get back to the overall reaction. All of the elementary processes or steps will give you your overall reaction when you add them up. In this case, we have one reactive intermediate because we only have two steps in this expression. The individual elementary steps of a mechanism are classified based upon their molecularity. The molecularity is the number of molecules or atoms that are involved in that individual step. So if we have a unimolecular reaction, that would mean you have one reactant. So we could imagine you have something decomposing or decaying. In this example, we have O3 breaking down into atomic oxygen and O2, which is molecular oxygen. But on the reactant side, we just have one species. So this would be a unimolecular reaction. A bimolecular reaction has two molecules or atoms or two things on the reactant side coming together. So here we have O3, which is ozone, combining with atomic oxygen to form 2O2. So we have two things coming together, O3 and atomic oxygen. A termolecular reaction would be where you have three things coming together. And notice we don't have an example. This doesn't usually happen. It's really hard for three things to collide with the correct orientations and the correct energies to actually combine at once and go to products. So you'll usually never see an elementary step where you have three things on the reactant side. So when we're predicting mechanisms, which is going to be our goal, we can start with a unimolecular or a bimolecular reaction, but not a termolecular reaction. We previously learned that the rate law for an overall reaction had to be determined experimentally. we couldn't look at the stoichiometric coefficients in order to write our rate law equation. We had to use something like the method of initial rates, look at all that data, and then figure out the orders to write the rate law. But it's a little bit different when we're looking at an elementary step. If we're just trying to write the rate law for one individual elementary step, we actually can look at the coefficients and the species that are involved in that step. So this wouldn't be the rate law for the overall equation, but just the rate law for that one individual elementary step. For example, if you have a unimolecular elementary step, we said that that means you have one thing breaking down essentially and turning into your products. We could write the rate law for that one step. We have A, and then there's a coefficient of 1 out in front of A. The rate law would be equal to R equals K times the concentration of A raised to the first order. And so that unimolecular process would have to be a first order reaction. If we have a bimolecular reaction, we could have one of two things. We could have 2 moles of A coming together. And so in this case, the rate law would be R equals K times the concentration of A, and it would be squared because essentially this is really 2A over here. And that would be one way to have a second order reaction for our step. The other way would be to have 1 mole of A coming together with 1 mole of B. And our rate law would be R equals K times the concentration of A times the concentration of B. Both of those raised to the first order, where the overall reaction is second order. We can only do this for those individual elementary steps. That's the key, where we're looking at the coefficients of that step and the species involved in it to predict what the orders are. Normally we don't do that. We have to use experimental data. But when you're writing steps of a mechanism and you're just thinking about what the rate of that individual step is, it's going to be dependent upon the species in there and the concentration of those species. When a reaction occurs in 2 or more steps, one of the steps will be slower than the other one. This is called the rate determining step or rate limiting step. Sometimes RDS or RLS is used for short, for rate determining step or rate limiting step. The step that determines the overall rate of the reaction is going to be the one that determines the rate law we'll see. So the step that is the slower step is going to impact the overall rate because a reaction cannot occur faster than that rate determining step. So the rate determining step will be our slowest step in a reaction. It's kind of like a bottleneck. The reaction can't go faster than the bottleneck of the reaction, which will be the slowest step. And so that's why it will determine the rate law of the overall reaction. So if we can figure out what our rate determining step is, we can figure out what the bottleneck is going to be, and that bottleneck will determine the kinetics of the reaction. So now let's try an example combining some of this new terminology and ideas about reaction mechanisms and individual steps. We're going to practice suggesting a 2-step mechanism for the reaction. Our overall reaction is H2 plus 2ICl forming I2 plus 2HCl. We also know our rate law, R equals K, H2 raised to the first order times ICl raised to the first order. So overall, it's a second order reaction. Recall if you add together the individual orders, that tells you the overall order. We also know a little bit of information. HI was found to be a reactive intermediate. So a reactive intermediate is produced in one step and consumed in another step. We want to predict for this reaction what our 2 elementary processes will be. So let's just rewrite the overall equation at the top, what we're trying to get them to add up to. And then we're going to predict 2 steps. At the end, our products have to be on the product side, our reactants have to be on the reactant side, and everything has to have the correct number of moles, and we have to obey the law of conservation of mass as well. So starting out, something that we can do is we can take that reactive intermediate. We know that HI was found to be a reactive intermediate, so that means that reactive intermediate will be produced in step number 1, and it will be consumed in step number 2. So we can start there. So now let's think about what could happen in the first step. It's unlikely that we're going to have H2 coming together with two molecules of ICl. Recall, this would be a termolecular reaction if all three of those things came together and collided at the same moment. So we know that's not going to happen here. So what could possibly happen? We have to make some HI. So if we had two molecules of ICl coming together at once, neither of those contain hydrogen. So that's not probably going to happen either. So what could happen is one molecule of hydrogen could come together with one molecule of ICl. And what could we form if that happens? Well, it looks like we're going to form some HI, so we're going to make some of our reactive intermediate. And we still have another hydrogen atom left over, and we still have another chlorine atom left over if we're looking at law of conservation of mass. So maybe we make one molecule of some of our product. Maybe we form some HCl. We have to start making some product somewhere, so we could form some HCl. And then you want to double check, does everything add up on the left and the right hand side? You have two H's on the left, you have two hydrogens on the right, one iodine on the left, one iodine on the right, one chlorine on the left, and one chlorine on the right. So we're obeying the law of conservation of mass for the first elementary process. Then in the second step, what could happen? The reactive intermediate, HI, could now combine with another reactant. We have one more molecule of ICl to use. We used one of them so far, but we have two from the overall equation. So HI could combine with another molecule of ICl, and we could form some more product. So looking at the right-hand side of the equation, we still have to make some I2, and we have to make one more molecule of HCl. So let's write down our products, I2 plus HCl, and then check our law of conservation of mass. So we have one atom of I, another atom of I, so two atoms of I on the right, on the left and the right hand side. We have I2 on the right, and then we have one atom of hydrogen here, one atom of hydrogen here, and one atom of chlorine on the left and one atom of chlorine on the right. So law of conservation of mass is good. Everything matches. We didn't create or destroy matter. And then when we add these up to double check that everything matches the equation that we were trying to predict the steps for, our reactive intermediates will essentially cancel. HI and HI cancels. And we're left with H2 plus 2 ICl on the left. These two will give us 2 ICl, forming I2 plus 2 HCl. This would be our 2 HCl. And that matches the equation we are trying to predict for. So these two steps are plausible to be our actual steps that this reaction could occur over. These are our two elementary processes. The overall that we wrote would be the reaction mechanism. So two steps in this mechanism. Now the second part of this problem says indicate the slow step. So when we're trying to indicate the slow step, that's talking about the reaction kinetics. Which step is faster than the other one? Which one's going to be our bottleneck for this reaction? And we want to think about, we could write those individual rate laws for the elementary processes and compare them to the rate law for the overall reaction. So we can write a rate law for step number 1 by looking at the reactants in step number 1 and the coefficients. So the first step rate law would be R equals K times the concentration of hydrogen, and it's going to be to the first order because there's a coefficient of 1 out in front in our first step, times the concentration of ICl raised to the first order because there's a coefficient of 1 in front of ICl in our first step. So that rate law for step number 1, notice it matches exactly the rate law we were given for the overall reaction. When this happens, this means that your first step is your slow step or your rate limiting step. That's the same thing. So our first step, the rate law matches the overall reaction because that must be the bottleneck. If those two species coming together with their same coefficients matching their orders, is the same thing as our overall rate law. That's because that has to indicate the kinetics of the reaction, and it's not going to go faster than that very first step where it matches. So in order for our reaction to actually occur, hydrogen has to collide with ICl, and that's going to be our slow step. The reaction will not go faster than that first step. It doesn't matter how fast the second step is. We can see that the overall rate of this reaction, based upon the rate law of the overall reaction, is dependent upon step number 1, which is why those two match. So when your overall rate law matches the individual rate law for step number 1, you can say that step number 1 is going to be your rate limiting step or your slow step. Let's try another example. We have a reaction, 2 nitrogen monoxide plus chlorine forming 2NOCl. We also know the rate law for the overall reaction, R equals K times the concentration of nitrogen monoxide to the second order times the concentration of chlorine to the first order. We were told that NOCl2 is a reactive intermediate. We're going to propose a 2-step mechanism and indicate what the slow step is. So our overall equation, we're trying to get our elementary processes to add up to, we'll rewrite on the top. And we're going to do this over 2 steps. We know that NOCl2 is a reactive intermediate. That means that it's something that's produced in the first step and consumed in the second step. So we can plug that reactive intermediate in to help guide us as to what's going to be happening in step number 1 and 2. So if we look at our overall reaction, 2 molecules of NO plus 1 molecule of Cl2. It's unlikely that a termolecular reaction will happen, so all 3 of those things aren't going to combine and come together at once. But a bimolecular reaction is highly likely. So maybe what happens first is 1 molecule of nitrogen monoxide comes together and collides with 1 molecule of chlorine. And if that happens, we have NO plus Cl2. All of those atoms add up to give us this reactive intermediate. So I'm not going to put any product down on the product side of step number 1 because I've already used up all my atoms with law of conservation of mass just to form that reactive intermediate. So then in step 2, maybe what happens is the reactive intermediate then collides with, we have 1 more molecule of NO we need to use up, so plus NO. And then we would have to form some product. We haven't formed any product yet. So we're going to have to make 2NOCl. We can check law of conservation of mass. We have 2 atoms of nitrogen. We have 2 atoms of nitrogen on the right-hand side, 2 atoms of oxygen on the left, 2 atoms of oxygen on the right, 2 atoms of chlorine on the left-hand side, and 2 atoms of chlorine on the right-hand side. So it's okay that we make all the product in step 2. So this 2-step mechanism adds up then to our overall equation of interest. Recall that your reactive intermediate will never be seen in your overall equation because it's on the left and the right-hand side. So you can think about it like it cancels out when you add them together. And if we were to write the individual rate laws for the steps, we can look at the species and the coefficients in there. So the rate law for step number 1 would be R equals K times the concentration of NO raised to the first order times the concentration of Cl2 raised to the first order. If we were to write the rate law for step number 2, that would be R equals K times the concentration of NOCl2 raised to the first order times the concentration of NO raised to the first order. Now if we compare the rate law for our overall equation that we were given to the individual rate laws, notice that our rate law for step number 1 and the overall equation does not match because in the overall equation, nitrogen monoxide is raised to the second order, whereas in our first step, it was raised to the first order. So in this case, the rate law does not match the first step. Now, does the rate law match the second step? It does not, because in our rate law for our second step, we have NOCl2, which is our reactive intermediate. Now, you're never going to actually have a reactive intermediate included in the rate law for an overall equation. It can't be in there because it doesn't exist for very long. It gets made and then it gets used up. So only the reactants of the overall equation can be included in a rate law. We could use algebra and rearrange this rate law for our second step, and it would actually match the rate law for the original reaction, but without including the reactive intermediate. So your overall rate law will never match step number 2 because you have a reactive intermediate there. But when it doesn't match step number 1, by default we can say that the second step must be the slow step or the rate determining step. Just because we don't have that reactive intermediate in our overall rate law, that's why it will never match step number 2. But your first check would be, does it match step 1? If the rate law matches the rate law for the first elementary process, then we could say that the first step is the slow step. If it doesn't match, because we only have 2 steps in these examples, then it has to be the second step that is the slow step. But remember, it won't match perfectly because of that rate law having a reactive intermediate in there. So that's why it doesn't match perfectly. But if you look, the rate law does actually match the overall equation. Notice there's a 2 out in front of NO in the overall equation, and the NO is squared. There's a 1 out in front of the Cl2, and Cl is to the first order. So it actually does match the overall equation perfectly. When that happens, your second step is also your slow step. So there's a couple ways that you can think about that. If it matches the first step, then that one's the slow step. If it doesn't match, then the second step has to be the slow step. A reaction has the following mechanism, and here we're given 3 steps. You won't ever have to predict 3 steps on your own, but since they were given to you, we want to say what would be the net overall reaction that occurs, and what are the reactive intermediates. So if we're going to figure out the net overall reaction, we would have to add up all 3 individual steps, 1, 2, and 3. But first, before we add them together, we want to see what's not going to appear in that overall reaction. So notice in step number 1, we produce N2O2. But then in step number 2, N2O2 is immediately consumed. So it's produced in one step and consumed in another. This must be a reactive intermediate, or an RI for short. In step number 2, we make N2O. And then N2O is also consumed in step number 3, so it's immediately used up. N2O is also a reactive intermediate. So when you have more than 2 steps, you can have multiple reactive intermediates as well. So now it looks like everything else is just either a reactant or a product. So we're going to add up everything on the left-hand side of the arrows with everything left over on the right-hand side of the arrows to write our overall change. So we would have 2NO plus 2 molecules of H2 on the reactant side, forming N2 gas plus 2H2O. And our reactive intermediates were N2O2 and N2O. So let's try another example where we predict the steps. For the reaction O2 plus 2NO going to 2NO2, the overall rate law for the reaction is R equals K, NO to the second order times O2 to the first order. N2O2 is found to be a reactive intermediate. We're going to propose a 2-step elementary process mechanism, and we're going to also indicate the slow step, or in other words, the rate limiting step. So our overall reaction is O2 plus 2NO forming 2NO2. We're going to predict 2 steps. Our reactive intermediate is N2O2, so produced in one step and consumed in another step. And so we're not going to have a termolecular reaction where O2 combines with 2 molecules of NO at once. Instead, what could happen? Well, we could have 1 molecule of O2 combined with 1 molecule of NO, but that wouldn't add up to our reactive intermediate if we had that. Or we could have 2 molecules of NO combine initially. So NO plus NO gives us, if we're looking at law of conservation of mass, 2 atoms of nitrogen and 2 atoms of oxygen. So that would add up to giving us our reactive intermediate, N2O2. We're not going to form any product just yet. We don't have any more atoms left over to make any product from step 1. And then in the next step, our reactive intermediate could combine with our other reactant we haven't used yet, which is the oxygen. So N2 plus O2 combining with a molecule of oxygen, and that would form our product, 2 molecules of NO2. And so checking our atoms, we have 4 atoms of oxygen on the reactant side of step 2. And we have 4 atoms of oxygen on the product side. We have 2 atoms of nitrogen, and we have 2 atoms of nitrogen on the product side as well. So everything works out according to law of conservation of mass. Our rate determining step will be determined from the kinetics of the reaction. So if we write the rate law for each of our steps, the rate law for step number 1 would be R equals K times the concentration of NO, and we have essentially 2 moles of NO on the reactant side, so it would be NO squared for step 1, and we could write the rate law for step number 2, R equals K times the concentration of N2O2, our reactive intermediate, times the concentration of O2, both to the first order. Now, looking at our rate law, first check step number 1. Does your rate law match step number 1? It does not. We have R equals K, NO to the second order times O2 to the second order. So you have a third order overall equation. And your first step does not match that. So if it doesn't match the first step, it doesn't match the second step either, but that's because the second step contains a reactive intermediate. So the second step must be our slow step or our rate limiting step for this reaction.